All right, so our next topic, inverses, and we will definitely not finish this today. It is not on your test Monday, okay, so don't worry about that. The only thing on your exam is going to be the graphing and analyzing rational functions that we just covered, your quiz. It's going to have the rational inequality, your sign chart problem, and compositions, okay, but it will not have inverses on there. So let's see. Graphs of inverse functions are reflections in the line y equals x. It's your linear parent. There we go. And you can tell from the graph over here, I went ahead and highlighted them in different colors so you could see it. If I were to fold this TV right along that line there, the two parts should come together perfectly. Okay, they're mirror images of each other. So any inverse you want to find graphically, that's our line of symmetry. And really what that's doing is taking the values of x and y, and it's going to reverse those. We'll talk about that in a second. Now, given a function f of x, the notation for the inverse function is, okay, Aiden says f with a -1. Yes. So this is how we would write that. So we want to say the inverse of function f or f inverse, and you could have inverse g, inverse k, you know, whatever variable you wanted to go ahead and use. I want to point out that, remember, that -1 is not a power. It's simply the way we write and let people know we're talking about an inverse. Okay. The domain of a function is equal to the blank. Okay, Aiden, say it again. Range of the inverse function. Okay. So the range of a function is equal to the domain of the inverse function. Yes. And I'm really getting kind of excited because once we finally get past this lesson right here, we are finally going to start getting the material that you have never seen before. We're going to start getting into trig, and I know everybody's really excited to get there just like I am, right? No more review. We want new stuff. Yay. Right, Dylan? I can see you're excited. Okay, he can barely contain himself. All right, if xy is a point on a function, then yx. Yes, and that is the core idea when we're talking about inverses. Elements of the domain, your x values, become the y values. So elements of your range, the y values become the x's. You simply swap them. And that makes sense when you take a look at the reflection that we just had. So whatever a function does as far as an operation goes, the inverse will undo that. It's going to have the opposite operation. So for example, if a function adds 3, then the inverse should in some way be subtracting 3. All right. If a function is dividing by 2, well, then the inverse should be multiplying by 2. It's always going to undo what the original does operation-wise. Now, to verify algebraically that functions are inverses of each other, you must show that. Does anybody remember this from Algebra 2? And it's why we did the previous lesson. Satish? Blanking? Aiden? Yes. Okay. She's saying this is where you have to take the function of one, the equation, plug it into the other, and simplify it to a value. So we're taking the composition. So f of f inverse of x. Now, what is it going to simplify to if they are truly inverses? X. Yes. And see, again, it's not a coincidence because y equals x is my line of symmetry when I want to find an inverse graphically. But the composition has to work both ways. So here, inverse f is going to be my inside function. It also has to work for f inverse of f of x. Okay, and that will equal x as well. And just because it works one way does not mean it's going to work the other way. It's very possible for the composition one way to give you x, but then when you reverse it, it does not give you x. So it's always a really good idea to go ahead and check both of them. All right. Now, if a relation and its inverse are both functions, okay, so nobody has gotten this one today, then both functions are. This is with respect to what we call the horizontal line test. Does anybody know what we call it? No, it's just a little phrase. Okay, maybe it'll be familiar once I go ahead and say it. We say it's 1-to-1. Basically, for every value of x, there is one value of y that corresponds to it. We say it's 1 to 1, and that's what the next part is talking about. So if each value of the dependent variable, we're talking about our x's, corresponds to exactly one value of the independent, okay, the y value, okay, passes the horizontal line test, then the function is said to be a one-to-one function. 1 to 1. All right. And if you don't know what that means, does that sound familiar to anybody? 1 to 1? Okay, maybe a few, maybe not for others. Okay. When we get to our next example, I'll go ahead and elaborate on what that means. Okay. So we have the vocabulary taken care of. Let's start getting into some examples here. Excuse me. It says for each of the graphs below, draw the line y equals x. You'll notice I've already got that here. Okay, there's my line of symmetry for inverses. All right, sketch the inverse of the function on the same grid. Then which of the functions are 1 to 1? Write the equations of each of the functions from the graphs, and then find the equations of the inverses algebraically. Okay, so let's go ahead and determine, let's call this graph right here, and what's its parent? What would the parent of that curve be? The square root of x. It's a radical parent, right? So let's call him f. Now, don't worry about, y equals x. That's just my line of symmetry. I want to take a horizontal line and move it vertically through this guy. So it's just like the vertical line test. The vertical line test tells me if it's going to be a function, right? The horizontal line test tells me if it's going to be 1 to 1. So as I take this horizontal line, as I move it up and down through the curve, am I ever hitting it in 2 or more places at once? No, right? So what would you say about this function? Is he 1 to 1? He is 1 to 1. Now this is really important, okay? Let's go ahead and get his equation, and then I'll explain why. Can anybody tell me what would the transformed version of that graph be? No, not the inverse yet. Just, we know that the radical parent starts here and curves up. Okay. So what brought him over here? Like what transformations? I'll tell you, there's no dilations here.
It's plus 3.
Plus 3 and then minus 2. Okay, now, I do have a question for you. The square root of x plus 3 minus 2. It looks like we went left and down. So why did we say plus? I mean, we went left. Yeah, remember when you're dealing with the x's, you have to either take the opposite if it's a horizontal shift, or the what if it's a horizontal dilation. The reciprocal. Okay, or whatever you're multiplying x by, you take the reciprocal, and that's your true scale factor. Okay, so let's see here. The reason it's so important for us to know if a function is 1 to 1. Hey. Okay. It's so important for us to know if these are 1 to 1. Well, think about it. The vertical line test is telling me if any values of x do what? If they repeat, right? Well, the horizontal line test is telling me if any value of y repeats. Now, why would that be really important for an inverse? Remember, what did I say was the core idea? What do you do with the x's and the y's? Hey. Part of band pictures? Or?
Yes.
Okay. Because with an inverse, you take the x's and the y's and you do what? You switch them, right? So think about it. If you have repeating y values and you switch them, they now become repeating x's. So if a function is not 1 to 1, that's telling me I can already predict that the inverse is not going to be a function. And we're going to say that our inverses do not exist if they're not a function. We'll say they're an inverse relation, but we really, really like our inverses to be functions. Okay? So I can guarantee that whatever his inverse looks like and whatever I find algebraically, guaranteed it's going to be a function. So let me go ahead and do this. We have -3, -2, so I'm going to go -2, -3. And my graph, my line of symmetry is not perfect here. You see, it's going a little off because my screen is stretched. Okay, so you see my y equals x isn't perfect. So this sketch is not going to be perfect. Okay, so just kind of bear with me here. So probably going to look something like that. Would everybody agree? Okay. So here we go. Now we know that f was 1 to 1. So if I were to take a vertical line and put it through this new graph that I just drew, what I'm saying is the inverse. You'll notice it passes the vertical line test. That inverse is a function. Okay, so that's why we want to know if it's 1 to 1 or not. So let me go ahead and make sure. Okay, so Savion just walked in. Raphael is now here. Did Shayna come in? No, Shayna's still in. Is she part of the band? No? Okay. And Alex walked in. Okay, so I got all three of them. Good. All right. Now let's actually go ahead and find what the inverse is. So how do I do that? Does anybody remember? Hey, Satish. There you go. He says change the x to y and solve for it. Hey, there she is. Okay. So he's absolutely right. In your equation, we know f of x is really representing an element in the range. The y, oh, don't forget the papers. Okay. So we're just going to switch the positions of x and y. So x is equal to the square root of y plus 3 minus 2. Once I solve for y, that's going to be my inverse. Okay. You guys remember doing this in Algebra 2? It's kind of coming back? Okay. So how do I solve for y? Okay, so I'm going to first add the 2 over. So x plus 2 equals the square root of y plus 3. Okay, now we square it because we want to get rid of the square root. So I'm going to square that quantity. Those are inverses, so they cancel. So x plus 2 squared. And I'm going to go ahead and subtract the 3 over so I don't have to write it twice. Minus 3 is equal to y. Okay. Now, you remember what I said at the beginning, that the inverse is going to undo whatever the original does. You're going to see the opposite operations. Like, for example, what's the opposite operation to taking a square root? Well, they're squaring it. See, we're adding 3. Here we're subtracting 3. Minus 2, we're adding 2. Now, a lot of times it won't be as obvious, okay, depending on how your function simplifies, but you should have those opposite operations. Hey.
So, for the first one, like say you plug in a -4 for x, it's not gonna work because you can't. It would be imaginary.
Yes. So this one right here, in fact, that's the next thing we were going to talk about was these guys' domains and ranges. But you're right. Yeah, if in the first function, if I plugged in -4, it doesn't exist on the graph because it goes imaginary.
The second one it does. So how do you?
The second one it does? Well, let's see. Okay. Well, let's see. What is the domain for f, the original graph? How wide is this curve? -3 to positive infinity, right? -3 to positive infinity. What's the range? Yeah, and again, don't be looking at, well, you know it's got to be -2 up, right? Remember, my graph is off because the screen is stretched when I went ahead and made this, so it goes, okay. So it should be from -2 all the way to infinity, right? Everybody's okay with that? Now remember, what are we doing with inverses? What are we doing with the domain and the range? We're flipping them. So the domain of this inverse should be the range of the original, -2 to infinity. And the range can be what? The domain of the original, -3 to infinity. So see, you were talking about -4. And see, it's true that's going to work. Because if I were to look at this guy just normally, I mean, he's a what? He's a parabola. But we're restricted by the original domain and range that we had. So while you're right, Jack, that -4 would work, he doesn't belong to this guy. Okay. In fact, that's one thing I do want to go ahead and point out. If your inverse is a function, then your very last step, you want to take the y out and go ahead and put in that inverse. Okay, notation that we use. Now, if it's not an inverse, we're going to leave the y the way it is. So this one is an inverse function. We really like our inverses to be functions. Okay, so at best, if it's not, we're going to go ahead and say it's an inverse relation, just a collection of ordered pairs. Okay, how we doing? Questions? Okay, well, let's try another one. And we might not make it all the way through this one, and that's okay. So this one, you know, the graph looks better. You can actually tell that y equals x is going through the points it should, because this screen was not stretched like the previous one. It's just how I had to do it for the snapshot. But let's see here. Let's start with the function. So let's call this guy f. Or do you want to try something different? Doesn't matter. Do you want to call him like g or q? Okay, let's just call him q. We'll say x. Okay, q of x, because we do have the axes labeled as x and y. Okay, but what is the equation for q? What have I done to that parabola? Yeah, it's just been pulled down too. So this would be q of x is equal to x squared minus 2. Now here's my question. Is he 1-to-1? No, he does not pass the horizontal line test. If I were to go ahead and draw a horizontal line, I mean, you can tell there's pretty much every spot I'm going to be hitting him in 2 locations. So he is not 1-to-1. So what does that tell me about the inverse? It is not going to be a function. Now here's the thing. We can make sure that the inverse is going to be a function if I restrict his domain. But I'm not going to show you that until next week. Okay? So right now, at best, we're just going to go ahead and say he's an inverse relation. So I'm going to take this off here. So is everybody okay? We're not 1-to-1. Do I need to elaborate on that? Okay. Let's go ahead and find his domain and range, and then I'll get somebody up here to go ahead and sketch the graph for me. How wide is this guy? Yeah, so he's infinitely wide, right? So his domain is going to be all reals. Okay, what about the range? -2 to infinity. -2 included. Okay. And see, do I already know the domain and range of the inverse? The inverse relation, I should say. Yeah. Okay, its domain should be the range of Q, and its range should be the domain of Q. We just swap them. Okay. Does anybody want to come on up and show me what the graph would look like if I did fold on y equals x? Okay, so many hands. Oh, just need one. Hey, when's our next game? Thank you, Dylan. It is tomorrow? Oh, next Saturday. Okay. Who are we playing? La Mesa. Saturday game. Okay. Okay. And what do you guys think? Yeah, I think that's great. You know, it's just a sketch. You know, we're not asking for anything perfect. If you are having trouble figuring out what your inverse looks like, you know, then I would recommend taking some points off your original function or original relation and then just swapping them. You know, plot enough points to go ahead and see what the guy looks like. But there is a little trick that I want to show you very quickly. What happened to my paper? I had a paper with a graph on it already. I think it's right here. Okay, here we go. Like this. Now, unfortunately, the people watching at home just have to kind of imagine what I'm doing, but everybody here can see what I'm doing. If you have a graph, any graph, and you want to see what his inverse is going to look like, if you take the top left corner of your paper, if you pull it across so that that corner becomes the bottom right. it'll always give you the graph of the inverse. Okay, every single time. So if you take the top left corner, pull it down, there you go. So then it becomes the bottom right. Okay, just like that. Okay. So just a little trick that always kind of helps. Okay. So let's see, what time do we have? I got 46. Okay. So I'll tell you what. Why don't we go ahead and stop there? I still need to go ahead and find his inverse, the inverse relation, I'll say. But we'll go ahead and do that on Tuesday. Remember, is this on your test? No, this is not on the test. Okay. All right, so let me go ahead and erase this and get ready for the next class.